Pahomov, and he will speak on fusible numbers and new results about this interesting combinatorial principle that has been announced just a year or so ago. So
okay, so let me start. So for people that haven't yet heard about the fusible numbers, let's start with this simple thing about them. So namely, consider the following function. Function n will be from reals to reals. And defined by cases, so it will be equal to minus x if x is less than or equal to 0, and it will be equal to n of x minus n of x divided by 2 if x is greater than 0. Okay, so this is a recursively defined function from reals to reals. Of course, it's not immediately obvious that this function is total. However, in fact, the function is total. But one needs a theory of some substantial logic thanks to prove this. Namely, for people that are familiar with second order arithmetic, so AC0 doesn't prove that n is total. Okay. Second, okay, of course we could restrict n to just two rational numbers. Then PA doesn't prove that n restricted to rationals is total. Okay. Yeah, so basically so both the statements are in fact true. Okay, then I keep standing somewhere here. I guess it's only the way.
You should simply.
Okay, yeah, it's also a solution to speak louder. Yeah, indeed. Okay, so this is an independent result. So this is actually this independence was this proved by Nivas. Ericsson and Su. So it's with okay. So they have preprint last year, and so very recently it was accepted through leaks, I believe. Okay, so yeah, so this is the independent result, and independent result. So I personally started to look at all this stuff about fusible numbers. So when I learned about this particular independence, so this I think it's a very nice one. So it's I think probably it's from a certain perspective, probably the simplest independent statement for piano arithmetic, in the sense that it's very easy to formulate, so you don't really need anything. It just gives this recursive definition, and so basically I don't know, high school students easily could understand what's going on. Maybe middle school student, but I guess okay, of course, school student probably wouldn't. This is what does not provable gains, but the statement itself should be perfectly understandable. Okay, so here we have this extremely simple result. So now let's look where from it was coming. Okay. Consider the this following set F. F is the least set such that first 0 is an element of F, and second if X and Y are elements of F, and X plus Y plus 1 divided by 2 is greater than maximum of X and Y, or equivalently the distance between X and Y is less than 1, then X plus Y plus 1 divided by 2 is also an element of F. So this is more or less standard way, more or less just a inductive definition of a set. So we have 0 is an element of a set, and so we have this closure under this operation as long as the result is greater than arguments. So this set is called the set of fusible numbers, and the reason why it's called this is the following. So namely, consider the following procedure to measure time. So we have fuses, all of them burn out in precisely 1 minute. However, internally the fuses are fuses could have internal defects, and so they not necessarily burn in uniform fashion. So you couldn't cut the fuse in two and guarantee that one half will burn in half a minute and the other will burn in half a minute. So basically the only thing that you could do with them is fire one end at some moment and fire the other end in some other moment, and then wait until the fuse will burn out. Okay, so now we are interested in the interval of time that could be measured using such fuses. For example, one could easily measure the, say, interval of time half minute. So if you fire a fuse from both the ends at the same moment, then so it will burn out in half a minute. And you also easily could measure the result of the interval of time of 1 minute. Yeah, right. And of course, how exactly the fuses are connected to what we see in the book? Blackboard is that basically if you fire the first end of the fuse at the moment X, and the second end of the fuse at the moment Y. So of course you could do it only if the difference between X and Y is less than 1 minute, because otherwise you couldn't really do the fuse will burn out earlier. Okay, so under this condition, so actually the moment of time when the fuse will burn out is exactly this. So X plus Y plus 1 divided by 2. So one could easily check that it's actually the case. And so other way to define the set of fusible number is a set of intervals of times that could be measured using such fuses. So basically, when you could have this kind of procedure when you start with say firing one fuse in some moment, then waiting some time and firing the set. Waiting the moment when some fuse burns out, firing some other fuse in one end, then maybe firing the other end of the fuse in some other moment, and so on. So this kind of complicated procedures, and this gives us the set of fusible numbers. So to give you some impression of how it looks like, of course 0 is an element of F. But this was expected. The next fusible number after 0, of course, is 1 over 2, because really how you could measure something less than half a minute using such a procedure. Then in fact it's 3 over 4, then 7 over 8, and so on. So basically we have this intervals of the form 2 to the n minus 1 over 2 to the n, so all of them, and then finally we have so it's what's happening here. And then finally we have the interval of time 1. Yeah, and so then it actually becomes more complicated. Yeah, so it's actually an easy exercise to check that indeed all this interval, so all these intervals in the set F. Okay, and so yeah, so the important observation about this set is that in fact it's a well-ordered set of the order type epsilon 0. So of course, which of course was very much motivating this previous independent result. So F is a well-ordered set with the order type epsilon 0. Okay, yeah, and so in fact, so if you basically the way how the previous result worked, so about this function n, was that one could, so basically this function n was this a function where that was a piecewise linear function with so countably many points of discontinuity. And these points of discontinuity, in fact, one could show that they were a subset of the set of fusible numbers. And this actually
which functions are piecewise continuous?
So
piecewise linear.
this is a function n from the beginning of the talk. And basically, I'm now briefly explaining why the function n, how function n was connected to this. So basically, I don't want really to go into all the details. One could look at Nivash, Errington, and Su paper. But so basic idea is that so
it's the next fusible number. Or
yes. So basically, okay. So basically, so this is set F prime. This is subset of F. Actually, it's proper subset. And then n of x is so if I remember this correctly, it was minimal of the epsilon greater than 0, such that x plus epsilon is an element of f prime. Yeah. So this. So in fact, n was this kind of function.
And f prime is what? Some subset.
Yeah, it's some subset. Basically, one could define it, but yeah, it's some kind of substantial analysis. But the point is that f prime is also has order type epsilon 0. And basically, there is a quite substantial amount of additional work one could show that in fact, so this is as an independence for K arithmetic, but I don't really want to go into this direction. So okay, so here, so basically this function n was very much motivated by the set of fusible numbers. So fusible numbers were the first. So this was, I believe, that was introduced by Ericsson actually in early 2000s. And so then it took time to actually people to notice them and to analyze. Okay.
What if you have f instead of f prime? No,
I mean you'd also would get a function, but it wouldn't have this very nice recursive definition. Actually, I think actually there's some not everything really known about this function. So one say get some more explicit definition of it, and maybe it's.
Yeah, well, I mean the set f, in contrast to f prime, has a very nice, understandable definition. As a kind of fusible number. So f is more primitive than.
No, I mean okay.
That function.
Right. No, I mean I would say that f prime is not that complicated. Okay, it's less. It's more complicated than f, but it's not that complicated. Basically, it's kind of you could define this kind of recursive way. If you basically you have this recursively defined function, And it has kind of this, and you could explicitly define, carefully define the set of points of discontinuity of this function, which is exactly the set f prime. Okay, but anyways, no, I mean, basically, what I think that there is this certain recursive definition of the set of prime. This could be given explicitly, but it will be just more complicated. But anyway, so
Okay.
Okay, so this actually the talk was not about the original constructive physical number. Now I want to talk about generalization. So to really figuring out what's really so going on here. Okay. Okay, so. Okay, so consider the following set. So let's first fix a function f from reals to real such that f is monotone. Monotone and yeah, so basically that's all. And by monotone I mean monotone in all arguments. So so if x1 is greater than y1, so on xn is greater than or equal to yn, then f of x1 xn is greater than or equal to f of y1, so on by f. Yeah. Okay, so we have this function f, so then we define this set G f. So it's inductively defined. So by the following process, so first 0 is an element of set Gf, and second, if x1 and xn were elements of Gf, and f of x1 and xn was greater than or equal to maximum of x1 xn. Okay, I think just wait. Then so f of x1 xn were an element of the set. So is the element of the set Gf. Okay, so this is the set Gf. And so now, and so one easy could see how to generalize the set of fusible numbers. So basically, if you take as f the function x, f, so if f of xy was x plus y plus 1 over 2, then the f is just the set of fusible numbers. Yeah. So, but basically, it's just the definition. Okay. So now we are getting to the first result. Okay, so okay, let's erase the last line. So sharing. Okay, so okay, yeah. So there's our result. So it's yeah. So of me together with Alexander Bevetov. So the theorem is that GF is well ordered. Okay, maybe theorem is based on understanding, so actually you'll see that first of all it's very easy to prove, and second actually the proof is just a simple generalization of what was happening in the case of fusible numbers. And the second part is, so it was announced as our results here. However, so since I was writing this abstract, I was in communication with Harvey Friedman, and it happened to be that actually Harvey noticed this and wrote about this on POM somewhere in the June last year. So actually, I think at this point we actually already knew this fact, but nonetheless. So basically, yeah. So answer is independently by thinking. Yeah. Okay. So now let's say, but again, so maybe it's just not that much important of a theory. But I guess it's mainly okay. Anyway, so first let us just prove it without any. Okay. So what would I write?
The top.
Yeah, I get it. Okay. So let's assume that everyone already remembers the definition. Okay. So I assume for a contradiction that F is not well ordered. Okay. Then let's consider the following number A. A is infinite of the limits of all descending chains in set Z. Infinite of so we have this number A, and of course, since we have at least one descending chain under our assumption that set is not well ordered, so we have this infimum is defined. And of course, since F consists of only of positive numbers, only of non-negative numbers, of course, so this will be some non-negative number. Okay, so notice that actually we could have a sequence of some particular form. Say, namely, we have A is equal to f of x by 1, so on, x I n, where all xij's are less than or equal to A, and of course all the elements of the set GF. So why we could find such kind of sequence? So where basically the elements of the sequence are this f of something that not strictly below A. Actually, it's very simple. So if we basically if we have some element above A, then we could so any element of the set GF is a value of term built of this function f and constant 0. And then basically when we have some number above f, so some element of GF above A, we can it corresponds to some term, and then we start to consider its subterms. And then we consider the shortest subterm such that its value is still above A. So and then we get some element of F that first is of precisely this form, so it's application of F to something that is non-strictly below than A. So because it was the shortest term.
Please excuse me, egoistic question.
Yeah.
Leonid Dmitrich, have you switched on the recording of the seminar?
Yes, we recorded it in a different,
Okay.
by different means. But we will see whether it works or not.
Yeah.
For interrupting.
Anyway, so basically we consider, given some number above A, we could consider the shortest subterm corresponding to this number, and it give us something of precisely this form, so something that is still above A. However, so the arguments are not strictly below A. And basically that's all. So basically, given some sequence, we just replace its elements by the shortest subterms, and strictly speaking, after that we could get something that is not not necessarily decreasing sequence, but it's still some sequence with the limit A, whose so considering of elements above A, and then you could just consider find some decreasing subsequence, and so get to what we. Basically it's very simple observation, in fact. So this was the first step, and now let's apply Ramsey's theorem. So this namely consider the following set of colors. So it will be the set. So basically we have this set of colors consisting of 3 to n elements. So each element is the result of comparison. And now basically we color pairs of natural numbers.
So the colors are from this power set of 3 symbols?
Yes.
Okay.
Yeah.
And what shall we color with this?
Pairs of natural numbers. So now.
Pairs of natural numbers.
Yeah. So assign. Yes. Assign to pair I j, where I is less than j, with a color. C1 so on Cn, where Cl is the result of comparison of xi xil and xjl. So basically our sequence is defined by this n sequences of numbers, so the sequence of first argument, sequence of second argument, and so on, sequence of nth argument. And then basically this column of pair ij is the following. We say it contains information about comparisons of is and this element of first sequence is this element.
I don't understand the following. Okay. What is this sequence that you consider? What is xil and xjl?
Okay, so this is what this
I understood that this was somehow variables xi something. They were just a set of possible values.
Okay, we
all such numbers.
Oh, okay, yeah. Oh, okay. Sorry, sorry.
Now you fix something.
Yeah. Okay. Yeah. Sorry, I lost a bit confusing. So what I mean is that we fix certain sequence of this particular form, whose limit is a.
Not necessarily ascending or descending.
Okay. It's okay. Actually, for this concept, I meant that it was descending, but for this construction, in fact, it doesn't even matter. Okay, so it's okay. Wait a second. No, okay. So
please write it on the blackboard instead of theorem Buffet of Pahomov.
Okay. No, I think it was. Okay, I think it was something. Okay. I think so, yeah. So the second thing about the sequence was that actually additional condition was that f of x I1, so on x in was greater than a. So for all I, so basically this the second condition for the sequence, right? So first we have this condition, so that all xij were below a, however all f of xij was above a.
Okay. So you actually added something to your previous statement. At this point.
Yeah, okay, yeah.
So we can say this, okay. And now what do you want to fix?
We fix a sequence of xij's with this property. So
a sequence of n vectors.
Yeah, okay, you could say yes, okay, it's other way to put this, yes.
Satisfying all these properties. The limit of it is a.
Yeah.
All the xij are smaller or equal than a, and that last condition.
Okay, yes. Sorry, yeah. I will skip the bit too much things.
Okay, good. Now this is fixed.
Yeah. So now
we introduce the coloring of pairs depending on the chosen sequence.
Okay, yeah. So basically now we right. So this is precisely what's happening. So we color pairs of natural numbers using this sequence of n tuples. And namely the color of pair ij is so this comparison of the corresponding components of this n tuples corresponding to index I and the index j. Yeah. So naturally it contains this n results of comparison. So we compare xi1 with xj1, and this will be the first component. So it will be less than if so xi1 is less than xj1, and so on. Yeah. So basically this is our set. Okay, and so now we apply Ramsey's theorem using to this coloring and obtain an infinite monochromatic set of naturals.
May I also ask the following? So your colors are sets or are they lists?
No, color is an n tuple.
N tuple. So it's an n tuple.
Yeah.
Okay,
So it was Cartesian power.
Yeah, okay, good.
Okay. Yeah. So I think.
No, everything is okay. Yeah. Now there's more discussion.
Okay. So let A be an infinite monochromatic set. For this particular coloring. And so, okay, so and it corresponds to certain color. So it's A corresponds to color. S1 and so on, Sn. Okay, so now appeared the following. Since all xij's were below A, neither of so S's could be comparison greater than. So because what would it mean if sum of components of this tuple was greater than? This basically would mean that the corresponding components of the sequence X on the set A would be an infinite descending sequence. So because it would be greater than would mean that elements with okay, let's write this. If SL was greater than, it would mean that X that for ij's from A, we would have that I is less than j. We would have xi and xil is greater than xjl, or in other words, L's component of our sequence was an infinite descending sequence when restricted on the set A. But we couldn't have this. So that all of them were in fact either equal or less than, or in other words, this corresponding sequences were monotonically non-decreasing ones. But since the function f was monotone, the corresponding sequences of xij's was monotonically non-decreasing. The corresponding of this f's of this applied to the n-tuples were monotonically non-decreasing contradiction. So that seems it was.
Now, could you repeat everything beginning from the let A be an infinite monochromatic set?
Okay, so let A be an infinite monochromatic set.
So what are you going to do?
So then we have this color S1, so on Sn.
Of this
set.
Mm-hmm.
Assume, notice that if some of the color was greater than, some of the component of this color was greater than, that leads to an infinite descending sequence in the corresponding index. So basically, if you consider this sequence, so we have this sequence xil, so where I was from the set A, and if L was corresponding to greater than, then the sequence would be descending one, and this couldn't happen because
fixed L.
Because A was the suprema of limits of infinite descending sequences. So this really couldn't be because, and this sequence was strictly below A. So this is not a possibility. So all the colors are in fact either equal or less than. And if all the colors are equal or less than, it means that all the sequences are either monotonically decreasing or constant. And this in turn means that this sequence of f's of these things will be monotonically non-decreasing because the function was monotone. So f was monotone, and hence this thing was non-decreasing. Contradiction with our assumption what the sequence was. So I assume it was infinite descending sequence. Okay, so this concludes the proof. So the here is fairly simple one.
Okay. And I suppose it will also work for several monotonic functions if you have functions f and g and then
right. Yes, yes, actually it will be relevant later than okay, I don't really have time for this. Anyway, actually it will be relevant later, so the same could be proved for finite remaining functions. So basically you could do the same definition when instead of just one function you have finite remaining functions. And then you could just generate the set, but so you have this. So instead of just one clause of the form 2, as in the definition of GF, you would have the same clauses, but for each of your finite remaining function, and of course this construction would work. Finite remaining function. Just the only modification of the proof would be that in this step you will need to fix a function. So basically we should have the same function for the elements of the sequence, but we always could do this. Yeah, okay, so this was the first. So actually I will have the second proof of the same theorem, namely as a corollary of Kraskov's tree theorem. Okay, so
so this was a corollary of Ramsey's theorem for pairs. Many kinds.
Okay, we have used Ramsey's theorem for pairs, but what I would say was important part of the proof was not Ramsey's theorem for pairs, but it was the principle that so basically there was this contraction we consider the number a's. So that actually there is this so infimum of the limits of all the standard sequences. So actually this was the crucial element of the proof, not the Ramsey theorem of in a sense.
Okay.
But this it was the element that was giving logical strength to this theorem, not like.
Okay, good.
Yeah. Okay. Yeah. So to remind you, so what Kraskell's tree theorem is. Okay. So. Oh, do I'm writing correctly?
Mm-hmm.
Okay. Yeah. Kraskell. Yeah. Okay, so to remind you, so we consider this finite trees.
Mm-hmm.
So tree is the set of finite trees okay. Then we consider embedding of finite trees. So f, so from T1 to T2, so T1 to T2 elements of the set 3 is an embedding, more precisely an inf embedding. If okay. Okay. So if f is an injective function, f is injective from nodes of T1 of T1 to nodes of T2. Okay, so the second f preserves the relation to be a child of relation to be a child and free f preserves the least common ancestor least okay, so what this means is that so basically if you have some bunch of nodes x1, xn, and so basically
Preserves the relation to be a child or the order relation? Because
order relation, yeah, right. It's wrong. Yes, thank you. Yeah, to be an ancestor. In fact, 2 will be a corollary of 3, but I think it's important to understand also because basically this 1 and so if you have 1 and 2, this will be the relation to be so as a notion of homomorphism. So it will be the notion of embedding of trees, and with 3 we will get the notion of inf-embedding of trees. And so this preservation of least common ancestors was basically the thing. The thing so basically if you have x1 and so on, xn from T1 and some xn plus 1 is least common ancestor of x1 from on xn, then f of x1 xn is the least common ancestor of f of x1 xn. Is the least common ancestor of f of x1, f of xn. So basically this is classical. So this is classical embeddings. So classical tree theorem says that the set of trees with an embeddability relation is a WQO. Or in other words, that any linearization of this relation, embeddability relation, is a well-ordering. Okay, let me state this like this. So classical tree theorem the embeddability relation then any linearization. Oh, yeah, let me slide. Is the ordering if L is subset of 3 and less than star is extension of less than equal to, yeah, so basically it's one way of stating this. So basically so if we have some set of our set of trees, and then we have a relation only that we build an extension of embeddability relation that is also a linear order, then corresponding so then this linear order will be a well-ordering. Okay, so other way to state it is that there are no infinite anti-chains in this less than order on tree. So this is the other way to state this.
And no descending chains.
Right, but it's more or less obvious for this order. Because so when you have infinite embeddability chain, so basically, because in any descending embeddability chain, your trees decrease in size. So if you start the tree with n elements, your chain couldn't be longer than n elements. So it's more or less triviality.
Okay, I thought you were giving the definition of quasi-order, but okay.
Yeah.
For this particular case, the second half is obvious, yes.
yeah, okay, anyway, yeah. No, I mean, it's a typical situation where basically when you have interesting quasi orders, at least the ones interesting in proof theory, typically the trivial part is is that so they don't have infinite descending chains, and the non-trivial part that they don't have infinite anti-chains. Okay, anyway, so basically, so now how exactly is it related to what we had before? In fact, it's the relation is more or less immediate. So giving, so if you remember, so in this set GF, all our elements were in fact represented by terms built up from the function f and constant 0. And then we could put in case, so given such a term, we could build up, we could consider it syntactical tree. And then basically we put this so basically then naturally our set could be considered as a subset of the set of trees. So then basically we replace element from our set by the syntactical trees of represented terms. And the point is that we get a linearization of Kruskal's order. Oh, more precisely, so actually I'm slightly lying because we need to slightly modify Kruskal's order. But so basically is this. So basically we take, so for such GF we take representing terms for all the elements, and then we take this syntactical trees of these terms. And this gives us this, embedding the Kruskal's order. Okay, so the part where I was lying was that basically we need to slightly modify Kruskal's order. So namely we need to add this additional clause that says that the order on childs is preserved. So basically some elements will say on the left. So basically, say two elements have some least common ancestor, and one element was say to the left to the other in the order of childs of this least common ancestor. Then this relation to be to the left of the order of child should be preserved. So if we need to this additional condition.
So we deal with ordered trees, not
we need basically to deal with this trees where we have the order on childs. And then this is basically our set GF is linearization of Kruskal's order. But basically the point is that from proof theoretic perspective, this modification of Kruskal's theorem doesn't really add anything. So we say the order type of maximal linearization of both the orders is the same. It's not that hard to show this basically. So simulate order on child in the trees that don't have order on child. It's basically could be done. Anyway, so basically this result is really closely connected to Kruskal's theorem. In fact, so one could even prove Kruskal's theorem by this argument that is very similar to how I can prove that the set GF is well-ordered. So yeah, this is really really two very close results. Okay.
Okay, what is clear is that if you have a term, you can. So what is not quite clear to me is this correspondence between points and terms. So,
okay, so
from term you have a point.
Okay, we choose. So for each point in the set GF, we choose any term that represents it.
Yes.
So, okay, obviously the term that's corresponding to this inductive procedure. So, so we could take any of them. So if there is no unique representation, we take just one of the representing terms.
Yes.
And then we get some linear order on these terms. And then hence we have this linear order on this trees. There's some set of trees that is a subset of this class, set of all finite trees. And the point is that this particular order will be linearization of Kruskal's order. And this is more or less follows in more or less straightforward way in basically from the definition of Kruskal order and the definition of and the fact that and from our inductive procedure plus the fact that f was monotone function. Basically, it's very much corresponding to each other. Okay, it's something that's really easy to check.
Yeah.
Oh yeah, should I go on?
Okay, let's go on.
Okay, yeah. Anyway, so we have this connection with Kruskal tree theorem. So now the question is, so what are the order types that we could get in the set GF? So in fact, Kruskal's theorem already gives us the upper bound. So namely, we know that linearization of Kruskal's order is a small Veblen ordinal. So to remind you, the small Veblen ordinal is the ordinal that you could is the suprema of the ordinal that you could express using Veblen functions with finitely many arguments. So if you remember what are those functions, yeah. So basically, any set of the form GF it couldn't have order type greater than the small Veblen ordinal. So this is we have the upper bound of what we could get here. But in fact, so we could, so it's easy to see that we could go as high as a small Veblen ordinal as well. So unfortunately, the proof is not very nice. So the examples that we get are not particularly nice. So namely, we just need to embed ordinals into rational numbers. Yeah. Oh, okay. Okay, so I think actually I don't want to spend that much time on this, so I will give an idea, but I guess if people don't understand some of the definitions, that yeah, then we'll just live with this. So basically there is so let's lambda so can be the small Veblen ordinal. So then we consider this the things called fixed point free Veblen functions. So this will be the function f prime.
What are we going to explain now?
So how to have the set GF whose order type is going to the small Veblen ordinal.
Okay, lower bound.
No, upper bound. No, yes, right, lower bound. So basically they could get as large as small Veblen ordinal. But basically, I don't think the proof is so particularly nice because it will be artificial examples, but they are quite easy to construct. So namely, okay, so we have this functions, so-called fixed point free Veblen functions. Yeah. So they are so basically what are they? So they are in fact monotone functions from ordinals to ordinals taken an argument. So if it would be if they would be so if you consider usual Veblen functions, they would be continuous. But basically, so there's this so-called fixed point free Veblen functions that are slightly modified Veblen functions, so that they break continuity. And they basically they're very similar to Veblen functions, but they so in the point where so there would be say so we would have some limit. Then so this Veblen function applied to the limit. So the limit would be fixed point for the usual Veblen function. But the small Veblen function, so the fixed point free Veblen function goes higher than the limit. So basically to the next possible value in the range of the usual Veblen function. Okay. Anyway, so I just don't really want to go into the technical details. So the point is, so what we do is the following. So and lambda capital is closed under this fixed point free Veblen function with any finite number of arguments. And so then what we do is we embed lambda into positive rationals in a discontinuous way. So, but discontinuous I mean so that if you have some alpha is limit of alpha 1, so alpha i's, so alpha I is less than alpha j for I less than j, then so all this will be f. So then h of alpha should be greater than the limit of h of alpha I. So basically we want to always, so if we embed this in continuous manner, that will basically preserve limits, and now we want to break the limits everywhere. So we go higher than this limit everywhere. And basically, we bet lambda in such a manner. Okay, yeah. And then we basically take this fixed point free wobbling functions on ordinals, and then it gives us this partial function on reals. And then we actually, so if you want, we given this partial function on real, we could say extend them to total functions. And in fact, so we could even say extend them to continuous total functions. And then basically this is our example. So if we take something, this function f.
So we should take as f
corresponding
phi prime.
Corresponding to phi prime, x1, xn. Then so order type of gf will be equal to phi 1 g n times. Yeah, so E is only words for n equal greater than or equal to 3. If n would be equal to 2, then actually it would get just epsilon 0. Okay, so basically, this is some technical details, and basically this is more or less the same what we get from this short restricted forms of Krasker's tree theorem. So this upper bar. Okay, yeah, I'm really sorry for people that didn't understand this part. But basically, my point was basically we take ordinals and we just embed ordinals, and this produces example. The examples are not particularly nice. Also, they could be explicit. So this is what is here. Okay, so how much time do I still have?
So when did we start?
10 to 7, I think. After all these discussions and trying to obtain the hardware.
65 minutes ago.
20 minutes.
Okay. Yeah. So. Okay. So now the next question that we started was whether we could have so nice examples. So basically what happens when so f is not something artificially defined, but some nice function. So for example, in the case of fusible numbers, we had just some linear function sf, and we could have epsilon 0. So how much we could get? And in fact, so I haven't used this before when I was writing the abstract. But as I mentioned, so I have this small correspondence with Harvey. In fact, Harvey had a conjecture, which actually we do disprove. So okay, so consider. So let me. So yeah. So basically so.
Did Harry also had this lower bound result in fun?
Oh, I don't know, but it's really simple. I mean, basically I think in his letters to FOM he haven't mentioned this, but it's easy to imagine that he would use that such thing exists. So basically he noticed this corresponds with Krasker's tree theorem. Actually, he also had some nice results of his own that haven't mentioned. So this some certain finite combinatorial statement that is equivalent to the finite version of Krasker's tree theorem. So he had some interesting observations in this lab. But not also. Basically, this wrong conjecture that he had was about this function. So namely, x1 plus so on. Xn plus 1 over n. So, yeah. So the question, of course, so this is natural generalization of fusible numbers. So, so for fusible numbers, n was equal to 2. So what happens when? So we have for arbitrary n's. So this Harris conjecture was that we get to slight ordinals as it would be possible to discuss theorem. So basically, for Harris conjecture would be that for n equal to 3, you would get something like f1 0 0 0. Right? But it happened not to be the case. So namely, let's call this function fn. Yeah. So the point is that ordered type of Fn is median ordinal of 5 5 and n minus 1 of 0. So we don't. So in fact, we don't get large ordinals with these particular functions. Okay, they are of course kind of large, but say much more than something that you would expect from cross-constructive theorem. Yeah, and so and so basically the result that we have is that if we have a linear function, so if f x1 xn be something like alpha 1 x1 plus so on plus alpha n xn where plus c, where alpha i's are greater than 0. Then GF then the order type of GF will be bounded by this ordinal. Yeah. So basically the function is very simple that we could get large ordinals. So yeah. Okay, so let me think. So do I really want to prove this? So the proof is not entirely trivial. It's that hard, but yeah, it's still requires some work. So I don't probably doesn't
say what it uses.
Yeah. Okay. So basically, right. So basically, we need certain property of this kind of linear functions. Okay, let's explain what was the property that we used. So the property is the following. So if you, so given some, suppose we have some function on one argument, so f, not f, but h, h from R to R. Okay, then consider the following set: a of h. That will be the closure of the set of okay, so it's kind of something like this. So H monotone. E of x, where h of x is greater than x. So we take the closure of this. So basically we take all the points such that the application function on them is greater than the point itself. Then of course since the function monotone, the same holds for iterative application, so basically the sequence of iterative application will be an increasing sequence. And then we take the limit points of the sequence. And then we take the set of all the limit points of such a sequence and take the closure of the set. So this will be our set h, AH. So now basically we given some multivariant function, we will generate families of function of function of one argument. Okay, so yeah. Okay, first let's define. Yeah. Suppose so now suppose HP of P is parametric family, a parametric family of monotone function monotone functions. Then we define A of HPP be a union of AHP for P from P. Yeah. So basically it's we just take the union of all the sets of all the elements from the family. And now given so as a set of given a multivariant function, we construct from it a family of parametric family of one variant functions. So namely, okay. So basically, okay. So now let us explain what the family is. So we have this f of x1, xn, and what we want to do is to fix some of the arguments to be some constants. So we have the function f and we have some set p. And now we consider the following set of functions. So namely we take, on some positions we take something like p1. So then so we get some. Then we replace the next variable with just x. Say the next say fix something next argument is something like p2, then p3, then we could again have x, and so on. So basically, what we do is basically, if we, instead of some arguments, we put a constant from p, and instead of other arguments, we put the same variable. And that we obtain from f this one variant function, so h of x. And basically, our parametric family will consist of all functions such a form. So basically, where we fixed some of the arguments with constants, and this diagonalized all the other arguments. Yeah. And so basically, so let's call this family S of f. Something like P, yeah, and then so what we take is something, we take the set A F S F P, yeah, so basically we can say, so when we have this possible, so P is this the possible set of these parameters, yeah. And then what the result is that basically, we're particularly interested in the situation where P is a well-ordered set. Okay. So that's the property that we want. So if P is well-ordered, then the order type of ordered, then the order type of this set, A of S of F P, is less than or equal to, okay, it's a bit, the next a bit arbitrary, so namely omega to the order type of P plus 1. Okay, so this particular expression is a bit arbitrary, so if we would have had some slightly larger order, it wouldn't really matter for the content. But the point is that basically, if we take this a bit strange of say transformation. So when we have a set of, so P, to recall it, so P was a set of possible parameters, and then for the set of possible parameters, we went to this family of one variant functions that obtain using these parameters from our function f, and then we went to the set of this closure of the set of this limit points of the orbits for this set of unary functions. And so and then we want to that this thing is a transformation of a lower set into a lower set with a increase of order types.
Okay.
Yeah.
Okay.
Yeah, and basically this is.
I mean, this is more details than we want to know.
Okay.
But nevertheless, where is it going? So
okay, so basically, now the proof works like this. So using this property, we show that any function for any function f.
We have this
okay, so for any function f that have this property, we have this kind of nice small ordinals here. So basically, if this kind of formation of sets doesn't increase order types to violently, then we get something nice here. And then we show that linear functions do have this property. Yeah, and the question that we still have, for example, is what other classes of functions do have this technical property about this information of order types. So this is a bit unclear. So for example, do all polynomial functions have this property? I don't think it's that difficult. We haven't tried that much. But still some open questions here. So, for example, could this theorem be extended to all polynomial functions, so all rational functions? And so, but I think so. The more important question here, of course, so when actually this theorem breaks. So when we actually, what are the simplest kind of explicit examples where we actually get this Kruskal style ordinal?
This inequality is actually an equality if one is allowed to take any linear function.
Wait a second, I haven't really thought about this properly. I haven't really checked this carefully. And but my guess would be that basically, if you do, actually, I don't know. I guess so for some, basically I think it's easy to yeah.
Question which
okay. The question was whether the theorem shows the upper bound, and I was asking whether for a specific, so you have specific linear functions for which this upper bound becomes exact.
Yeah.
So apparently, if you have just binary n equals 2 and then the function f.
No, okay, so
2, then you have epsilon.
Yeah. Okay, so for this
0, which is phi 1 of 0.
Okay, for particular Friedmann functions, the bound is exact. So we do know this. But I think basically it's something that's very easy to figure out. So what I think would happen either you have some. So basically, if either this proof of the lower bound does work, or it breaks for fairly trivial reasons. And I probably want to just figure out some kind of inequalities on alphas such that so you get your ordinals say phi n minus 1 of 0, maybe you get something like phi n minus 2 of 0 under certain conditions, and so on. So basically something like this should happen. But I am almost sure that this should be something very easy to figure out.
So you're saying that it is easy to figure out for a particular linear function?
No, I think general study would be I also do quite simple. So
okay.
Yeah, but what I think is that the reason why the segments will break will be simple reason. So for example, if the growth rate of this function is too high, you will get something very small. For example, so if if this wait a second. Right. For example, if all alphas are greater than 1, obviously you will get the set with the order type omega. So because what happens, you will just very fast go very fast to this. So basically, so when you iteratively apply your function, you just fastly get larger and larger numbers.
Okay.
There's no way to get something.
So you are thinking about a better result where you say that for almost all linear functions, except for a few exceptions that fail for
I say that,
you will have the same.
No, I think basically, so one could say get some linear inequalities on the coefficients alphas and constant c, and say that so if some inequalities holds and this bound is exact, and basically so then if some other inequality holds, then you have some other bound, and some other inequality you have some other bound, and basically you just say have this full classification. I think this is completely doable.
Okay.
But I haven't done it. Maybe my intuition is wrong, but I'm almost sure that's true.
Okay.
So I think it's more or less all I wanted to say today.
Okay, very nice. So, other questions of the audience? So, let's see. Is there in the chat?
Maybe not just a question, but a remark or modest proposal. I've already talked to Fedja. Can you hear me?
Yeah?
I've already talked to Fedja, but let me repeat for all. Maybe it would be interesting to look at functions of arbitrarily many arguments.
Yeah? But basically, right. So I think in the years actually mentioned one generalization for this. Functions, for example, if you have a function that could take, say, finite sequences of arguments, and then you have this property that f of so basically this kind of property. So f if so
you can raise.
Right. Of course, sure. So basically, if you have so this function that takes some sequence of arbitrary lengths. So this is when n varies. So then if you have this condition that less than or equal to f of then the theorem would hold for such a functions. And of course we need this monotonicity when we have fixed number of arguments. So, but basically this is all just say variations on Kruskal's theorem, because of course this form of so here this theorem corresponds to this particular form of Kruskal's theorem where we have say trees without marks in the nodes, but then for more general values you could mark nodes with elements of some well-quasi ordering. And this will be slightly stronger version, but it's kind of not that much stronger. But you could do this, and then you could get slightly stronger results.
Okay.
So what I think would be interesting to research here really, would be to find something similar that corresponds not to Kruskal's theorem, but say for some stronger forms of really stronger forms of Kruskal's theorem. For example, there is say Kruskal's theorem with gap conditions, and if something would figure out how gap condition would correspond to the classes of functions, and so I think one could get some nice new independent results from this for some much stronger series of second order arithmetic, some above pi over 1 comprehension, and so on. Because Kruskal's theorem is of course a bit.
Of course, the idea that Kruskal's theorem is used to show that some, let's say, applying Kruskal's theorem to to tree made of terms is pretty standard idea.
Yes, of course,
This is of course the classics. What is interesting here is that very nicely it is mapped to the real life, so to say, and somehow without too much loss of information, as we see. Yes. But I have not seen any examples of using this tree theorem with gap condition.
Yeah, I don't know. I just speculating. I don't know.
Yeah, maybe if you consider some generalized version of terms which would be considered rather as graph, you would apply.
No. I mean, no. No, I think we should have usual terms, but we should somehow you need to have say interpret gap conditions as some kind of nice condition for function on the real line. But maybe it's not, maybe the condition function in real life wouldn't be nice at all, and yeah, then what really is the point?
Yes. Gap condition corresponds to some ordering of, so when you see the situation that you have, let's say, n different functions, you have some ordering of this function in terms of strength somehow, and then you, some functions subsume the other functions, and so in that kind of
but
arrangements
for example, maybe what there is some natural functions from reals to reals that somehow have this gap condition, and then we get some very light choices. I don't know. Again, this is just speculation. I don't know.
Okay. Of course, it's interesting that this principle was invented not by people who searched for independence results,
right? Yes.
But rather they discovered this nice, well-ordering structure. Of this set. How do you call it? This fusible
number.
Fusible number.
So actually.
I
think that they was
once you have that, you can sort of get all kinds of results.
I think the basically they was targeting the wrong audience because so that's interesting how I actually learned about this fusible number stuff. So maybe I have a colleague so I have my classmate that now works in Google, and he sent me the link to some post at Mastodon. So the one the author of this paper, so Gabriel Milash, wrote about this function n from which I started. So it was and this is
not about referring their paper.
Yes, I was referring the paper later, but
Okay.
Yeah.
So you learned about it prior to that?
No. Yeah. It was So basically from my friend that works in Google and does nothing in logic. So
okay. Anyway, a very nice result, and we'll remember the talk by Nivash. Maybe we should have invited him to listen to your talk. Did you write him about these results?
Oh no! Probably I should. Yeah.
Definitely should. I think he might be interested. In fact. Good. Any other questions or remarks from the internet audience? Sorry again for the late beginning of our seminar.